Have you ever tried to explain how to do something really simple, like tying a shoelace, to someone who's never done it before? Now imagine trying to teach that to someone or something with tentacles instead of hands. It sounds kind of impossible, right? Well, that's pretty much the challenge robotics engineers are up against. Today, we're going to dive into a brand new approach that teaches robots with completely alien bodies how to do human tasks, not by watching, but by feeling. So that's the big question, isn't it? How do you possibly bridge that gap? How do you teach a hand that looks like it's straight out of a sci-fi movie to do something as delicate as, say, screwing in a light bulb? As we're about to find out, it is definitely not as simple as just saying, hey, copy what I'm doing. And this picture, this just says it all. On the left, you've got the teacher, a human hand, perfectly tracked in virtual reality with 5 super complex jointed fingers. And on the right, you have the student, a soft, air-powered gripper with just 3 simple, kind of blobby fingers. I mean, the shape, the way they move, even the number of fingers, they are just worlds apart. This whole issue, this fundamental challenge, well, in the world of robotics, it actually has a name. It's called the Embodiment Mismatch problem. And it's just a fancy way of saying what we're all thinking. The teacher's body and the robot's body are radically different. Let's break that mismatch down a little more. You know, a human hand has a rigid skeleton, dozens of joints, and this incredible fine motor control. The soft robot hand on the other side, it's kind of squishy. It's driven by air pressure and it moves by deforming and bending. So trying to do a direct one-to-one copy of finger movements is, it's pretty much impossible. And you don't have to take my word for it. The researchers behind this work put it perfectly. They say that kinematic matching, which is just the technical term for trying to copy the exact poses and movements, is often ill-posed and insufficient. What does that mean in plain English? It means just telling the alien hand to mimic the shape of the human hand. It just flat out doesn't work. It completely misses the point, the function of what you're trying to do. All right. So if just copying the look of a movement is a total dead end, what's the solution? Well, this is where a really cool new framework called SoftAct comes into the picture, and it proposes a completely different way of thinking about teaching robots. And here it is, the whole system in one diagram. Now, I know it might look a little complicated, but the idea is actually super elegant. It all kicks off on the left, where a person puts on a VR headset and shows the robot how to do a task. Then it goes into this middle box, the force-aware retargeting. This is the secret sauce, the magic translator. And finally, that translated skill gets sent over to the real-world robot hand on the right. So let's unpack how that magic box actually works. And here it is, the absolute key, the big aha moment of this whole thing. The big idea behind SoftAct is to stop obsessing over the look of the motion, the kinematics, and start focusing on the forces, the feel of the task. It basically says, I don't care if the robot's fingers look like the humans, as long as they are applying the right pressures in the right spots to get the job done. It's all about the feel. Okay, so that's the concept. But how does it all work in practice? Let's zoom in on that force-aware retargeting block we just saw and really understand how SoftAct teaches with force instead of just copying form. It all boils down to this really clever 2-stage process. First, there's an offline stage. This is where the system sits down and studies the entire human demonstration to figure out the best way to assign the robot's 3 fingers to do the work of 5. And second, there's an online, real-time stage where the robot is constantly fine-tuning its grip as it's actually doing the task. So let's take a closer look at stage 1. In this picture, you can see the human hand interacting with an object, and all those little red arrows, those represent the contact forces that were captured in the VR demo. The system analyzes the distribution of all of those forces. It figures out, okay, the thumb and forefinger are doing most of the heavy lifting here. Then it intelligently assigns the robot's 3 fingers to balance that exact same workload to get a stable grip. It's kind of like a conductor assigning parts to an orchestra, but for physics and force. And now for stage 2, the real-time adjustment. This 3D mesh might look a little crazy, but it shows us something amazing. The blue dots, that's the human hand from the demonstration. The red dots, that's the robot's fingertips in real time. See, as the robot moves, it isn't just following some pre-programmed path. It's constantly looking at where the human made contact and making these tiny little adjustments, pulling its own fingertips towards where the human applied force. It's literally feeling for the right contact points to keep a stable, functional grip, adapting on the fly. So the theory sounds incredible. It makes a lot of sense. But the real question is, does it actually work? Well, the researchers put SoftAct through its paces, comparing it head-to-head with the old school just copy the movement methods.
And yeah, the results are seriously impressive. Here you can see that three-fingered soft robot doing one of the trickiest tasks imaginable, screwing in a light bulb. I mean, think about it. That requires precise, continuous contact and force control. It's something that's basically impossible if you're just trying to copy a human hand shape. But by focusing on the feel, SoftAct nails it.
The numbers tell an even more powerful story. In the simulations, the jump in performance is just dramatic. Take pouring from a paper cup. The old method only worked 40% of the time. SoftAct, 90%. How about reorienting a box? It jumps from 30% all the way to 90%. Unscrewing a bottle, nearly double the success rate. It's a huge leap across the board. But this is the one that really gets me. The light bulb. The old kinematic method, the one that just copies the pose, had a success rate of 0%. It failed every single time. But SoftAct, by focusing on contact and force, succeeded almost half the time. It literally took a task from impossible to possible. And the researchers' own conclusion just sums it all up perfectly. They stress that the key to teaching these alien hands isn't just better imitation. No, you have to model the contact and the forces. That crucial information, they say, simply cannot be recovered through kinematic imitation alone. So, okay, this is obviously really cool for robots that need to screw in light bulbs. But what's the bigger picture here? Why is this breakthrough so important for the future of robotics?
Well, the takeaways are actually huge. First, this blows open a whole new door for teaching all kinds of robots with non-human bodies, not just soft grippers. Second, it shifts the entire way we think about teaching, moving from just dumb imitation to a real, functional understanding of a task. This means we can start trusting robots with delicate, contact-heavy jobs we'd never dream of before. And finally, because it's based on the real-world physics of force, it helps skills learned in a simulation actually work in the real world, which has always been a massive headache for robotics.
And this all leaves us with a really fascinating thought to chew on. For so long, we've taught robots just by showing them what to do. But now that we can teach them the feel of a task, what other complex, delicate human skills, everything from surgery to playing an instrument, could they finally be ready to learn?